Go.
Hello
Hello and welcome back to Differential Equations, section 1.67, population models. 1.7. I'm not starting over. We already discussed the basic population model, which you get from the sentence that the change in population is proportional to population. And we probably also mentioned that it was garbage, right? So the change in population in time is proportional to population. And then over here, insert work, which is separation of variables. And we get that population in time is equal to initial population e to the kt. Now, so we did this problem on day 1 of differential equations class. And we came up with this model, which is given to you, let's say in PreCalc. You can compute locally, but on the long run, this particular model is not good because the limit of P0 e to the kt as t goes to infinity is infinity. It's the population growth, exponential growth in time, and we know that population cannot be infinite because the surface of the planet, whether you're talking about bacteria or rabbits or people, the surface of the planet is finite, and you can fit finite amount of units. Now, whether it's 15 billion or 30 billion, well, you know, it's definitely not infinity. Now, the question is, can we do better? And the answer is sure. There are other population models that will take into account birth rate, death rate, sick rate, war rate, right? And all of these other things that we can add to the model, which necessarily creates more difficult equations, but once they're solved, those models are far better. And we are going to consider some of those models. Mainly, these types of models are all already solved. So whether you are remembering the outcome of those calculations or you are deriving everything from scratch, it's completely up to you, right? Each one has its own perks or drawbacks depending on where you stand. So we can start by looking into introducing terms for birth rate in time and death rate and time. We are going to use Greek letters, B and D, which are beta and delta. So beta is B, and that's going to be birth rate, and then delta is death, which is the death rate. So we can introduce these concepts as function beta of time, obviously, number of births, per unit of population, per unit of time at time t. Oh, there's too many times in units here. And delta time is number of deaths per unit time population and so on. So thinking about this is earlier in our model, the birth and death rates and conditions of living and everything was mushed into this constant K. For your Newton's law of cooling, the type of oven you have is in that, right? And the dish that you are using for baking and everything else is together combined in reflected in this constant K. For population, as I said, birth, death, conditions, and everything else in that same constant. Now we can redefine our differential equation, and we would say that the change of population in time is given as the birth rate minus the death rate times the population. So it's proportional to this situation. So that would be what we define as the general population equation. And one more time, as you can see, it contains birth rate and death rate as the separate entities rather than mushed all into one constant K. Now, yes, you can define constant K as beta minus delta. That reduces the problem to what we had before. And we would have, right, the same separation of variables to solve everything and move on from there. Observe that separation of variables here is still something that you can do. Your variables are t as the independent variable, time, and population. So this is still solved by the separation of dp over p equals to beta minus delta dt, and then integral on both sides, and you're done. Now, this beta and delta are functions, so clearly it's not just going to end up being e to the kt. You are going to have more interesting cases. So I will just say use separation of variables to isolate p's and t's. So you will figure it out. As an example, the textbook is giving you the alligator population. It says suppose that an alligator population numbers 100 initially, so there's your P0, and that the death rate is 0. So I guess, oh yeah, that guy, the crocodile guy died, right? Fish killed him.
Yes. But not by a crocodile.
Yeah, I know, fish killed him. That's the... alligators, crocodiles, are kind of close. They look the same. He would poke it with a stick anyway. So, and then we have the birth rate, right? So we are going to have a population model from there. So suppose that an alligator population is 100 initially, and then you have the death rate is delta is equal to 0, and then the birth rate is beta equals, right, something. Now you have to model that. You have to look at the death rate and the birth rate, and you model those functions first, and then you plug those in the differential equations. In differential equation single. So initial population is 100. The death rate is 0. The birth rate, well, we are getting new ones. So P, right? And when you plug this in the general population equation, you are getting that the change in population of alligators in time is going to be beta times the P from the equation is 0.0005 P squared. And I'm just going to say separate. I don't want to waste your time. separate vars, and you can quickly come up with the same thing. Now,
Where do we get the p squared from?
you have a p in beta, and you have p in the equation. P times p is p squared, right?
Oh, okay.
Are we all agreeing on that? So this delta here, sorry, that's death rates. The birth rates have p, and then you are multiplying by this p. P times p is p squared. Once you solve the problem all the way, you get that the population of these alligators in time is 2,000 divided by 20 minus t. And that is the general solution. I really hope that you guys will go through the calculations once you review your notes and make sure you can do the separation of variables where you take the p squared, put under dp, dt to the other side, integrate, right, and work it out. Now, yes?
No, I was just going to say when you integrate the 1 over the p squared, it's negative 1 over p because of...
Yep, it's a plus 1, yep.
Plus 1.
And now we move to the next step. We are going to make the model better. Remember, we started with the ideal case, which was complete garbage because right infinity pushes you to infinity. Observe what happens here. Remember how I told you that you should use the limit to see if the model is any good? What happens as the time goes to infinity in this case? How many alligators do you have? Yeah, which is inconsistent.
Yeah, right? What happened?
Because didn't they say that the death rate is 0? Yeah, so what happens? So you see that the model is not really good one. So use the limit to your advantage to try and see how well the model actually does.
So that's a bad model.
Of course, that's why we're going to make it better now. So the next step is, well, isn't it true that the more population you have, the more competition you have for resources and food and stuff, right? Which makes sense. So that has to introduce another factor, right? And now our model is going to have the birth rate and the death rate and then the competition, right, involved as well. So we are going to now say that in situation, right, as diverse human population of nation, the birth rate beta is a linear decreasing function of population P, and the death rate stays constant. So we're not going to introduce wars. Let's say we are distributing food evenly and then just certain amount of people don't make it. Well, because they're allergic or something, I don't know. So now the model is going to change. They have, again, notation. Let me just pick up all of the things. So now beta Oh, there it is. So beta is equal to beta 0, right, initial case, minus beta 1 times p. So this is your new birth rate function. It contains two constants for the birth rate. You see that one of the constants is related to the original population. So this is the term which involves the reproduction. And the first term over here deals with the available resources. We can talk about food, we can talk about whatever, I mean, depending on the population. And the death rate is going to be constant. Right, so the example of that is texting, for instance. Well, for the lack of the better. So now, when you plug all of this in the differential equation, we're going to have beta 0 minus beta 1 p minus the constant death rate times p, and you distribute everything, you get beta 0 minus delta 0, those are the constants, minus times p minus beta 1 p squared. So I combine the constants beta 0, delta 0, and multiply by p on the outside, and then minus beta 1 p times p is p squared.
Hold on, it's all copy. Are you just like distributed through?
Yes, and I put these guys together, times p, and then I also, right?
Yeah, there we go.
Yeah.
So when you give us the number
Now, we are going to call this a new A and B, both of which will be larger than 0. And then we get to the point where we have the new population model, which is actually going to be a good one. AP minus BP squared. This model is a good model for population. It's called Logistic Equation.
This is used always, or it's just
Well, this is the one that we can use. The reason, so once you solve this, you are going to get, crazy looking solutions. We are going to solve one of these, obviously. But then, what's interesting is to see the graph of this one when A is larger than 0 and B is larger than 0. So when this happens, population model looks like this. This is your time, this is your population. It's going to start at P0, right? Initial population. It's going to rise exponentially, and then it's going to level off. That makes sense. So this is how solution is going to look like. It makes sense because you have initial population, you have explosion in population over time, and then all of a sudden, competition for food, competition for energy, competition for space to live, and that competition could be just, let's not have more kids, or it could be worse. It doesn't matter. It's just population at that point is not changing rapidly, and you pick the method. Well, you can also approach from the upper side, which means the population can decrease and then keep steady, because they are going to reach the steady state. And this line that they are reaching is the carrying capacity. And you get that as a limit.
Japan's population is decreasing because nobody's making babies.
Yes, they're overpopulated, but
And they frown upon immigration. They're going to have a population problem in a generation or so.
well, they're 10th largest, right, population on the planet, and they have those 4 tiny islands. I have no clue how they fit, but they fit somehow. I think they have 100-something million.
Yeah.
So they have 1/3 of United States in terms of population, and they have whatever barely amount of. Come on, it's differential equations. So now the population model is better, and the equation for this necessarily looks much crazier than what we had so far when you solve it. But again, it's not impossible to solve it. So let's take a look at the problem where, again, differential equation is given to you, and now you have to solve it somehow. So this is differential equation that is given to you. Now, you know that you need to do separation of variables. You have multiple p's over here, so you are going to say dp over dt is equal to, you multiply this out first to get 0.06p minus 0.0004p squared. And now you are ready to work on separation. So you have dp over dt, dp over 0.06p minus 0.0004p squared. There we go. Equals to dt. Right? So now equation is separated, hit both sides with the integral sign, and then what are we going to use?
Separation we did that already. Integration by parts.
Nope, and nope, and nope.
What do you mean we're going to use?
There we go. Partial fraction decomposition. So insert partial fraction decomposition. There we go. And after all of that beautiful, beautiful, beautiful work is done, partial fraction decomposition says ln p minus ln 150 minus p equals to 0.06 t plus c. Now you will combine this as a division. Ln p over 150 minus p is equal to 0.06 t plus c. Then you e both sides to give you p over 150 minus p equals to e to the 0.06 t plus c, which is awesome.
So we're just copying this, but are we missing a lot of steps that we need to see, or no?
Well, there is a partial fraction decomposition part here
all the way
from
through.
Calc 2, and the rest of the steps I am putting in all the steps for. And then there's this algebra piece. So now you need to solve this for p, right? Because it has to be population equal everything else, which means that now this guy multiplies there. So p is equal to 150 minus p times e 0.06 t plus c. I can actually break off this plus C, and what they use? They use B, whatever. I'm just going to circle this plus C and point down to B so you know what it is. And at this point, you have to add this P to the left-hand side. So you have P plus P times BE 0.06T.
That's a regular thing, not the P birth rate thing. That's the point.
Yeah, this is just a constant. I could have put capital K, but I'm going to use the same notation as the textbook, so it's not confusing. 150 B e to the 0.06 t. Factor out P, 1 plus BE 0.06 t equals to 150 B E 0.06 t. And we also have, when t is equal to 0, P equals P0. So you can figure out the value for B. Plug everything in. 3 dots meaning skipping those steps, so plugging everything in so I'm not writing arithmetic. Here's the logistic model. 150 P0 divided by P0 plus 150 minus P0 e to the negative 0.06 t. This is the solution. P0, initial population. The rest are all constants. P of t, obviously, population at any time t that is given. So now if this was measured in years, you can say, okay, what happens in 20 years? You plug in t equals 20. If you're talking about bacteria, it could be hours, right? So what you do here is you just solve the problem. Solve the problem from pre-calculus point. You already seen the graph, so you know what the graph looks like. And oh, perfect, that's exactly what I was waiting for. What happened? About 4 feet from the wall in the middle. Oh, but he asked.
The very first equation, that's the one given.
Thank you.
P quantity 150 minus T. The very first equation, that's the one given.
Yes.
Okay.
I can make it difficult if you want.
No, go ahead. Might as well.
Now, we would like to consider what this entails here, right? How do you find carrying capacity? That is the key question for a problem like this. You send this limit to infinity and see what pops up. So to find, here I'll do it in blood. Carrying capacity. It's going to be limit, time goes to infinity of P of t. So we're going to take our solution, our model, and we are going to hit it with the limit. T goes to infinity. 150 P0 divided by P0 plus 150 minus E to the negative 0.06 t. When you plug in t goes to infinity, you get e to the 0, and e to the 0 becomes 1. Sorry, you get e to the negative infinity, and e to the negative infinity goes to 0. Much better. So that kills this entire term goes to 0, and you are left with the limit. You are left with 150 P0 over P0, and we get 150. So you see that for this problem, whatever it was, we have carrying capacity of 150. Yes?
I looked at the top here, because I wanted that essentially what we're doing. And can the carrying capacity just be 1 0? That makes sense too. So it's not just one levels out, right?
Yes.
So do we have to? Okay.
Actually, the carrying capacity was in the original equation. Yep.
Yeah. That's
Mm-hmm.
really it.
Mm-hmm.
How do you see that? How did you see that? I know we do.
But
It's a real question. Just kidding.
the carrying capacity is actually worked out in the equation, because that gives you the upper limit of how much population you can have because of the resources. The same equation can model the spread of infectious disease, which is the maximum amount of people that can be infected and affected by that disease. For instance, I mean, we're here, right? There were plagues and plagues and plagues before certain people would be immune to that. Never in a situation in the history, right, taking certain books aside, was an extinction, right, for the human population, right? And you have like one person survive. So the carrying capacity would say that, let's say, in a town population 28,000, the carrying capacity, right, which is the people surviving flu or some kind of crazy virus, right, the carrying capacity would be whatever is remaining. And that's actually worked out in the equation.
Because it was given.
Yes, but it can also be calculated. It can also be calculated through different means. You consider, I believe I talked about it, or maybe I talked about it in Calc 2, I don't remember now. Carrying capacity of the planet, you would look into resources of the planet. You would look at the amount of food, the amount of energy, the amount of available space to live, and then you go nation by nation and you average them all out. So apparently, the 15 billion carrying capacity of the Earth was computed through the considering the national GDP or something of Uganda, because Uganda turned out to be the average. Like whatever they had was the average for the entire world. On one end, you have United States as still one of the richest countries for now on the planet, and then you have Nepal, where people live $1 a day. So it's huge disparity between the two, right? So when you look at, and then you take all of the nations into account, you have very well developed Europe, you have US and Canada, and then you have on the other side a lot of African countries and so on. I mean, China is developing at an insane rate, Brazil is developing at an insane rate, but then like India as well. But then you have other countries to average that out. There are, you know, well, that's the active other.
How about when you, I don't know if it was in this one or that other book, when you read that they say by like 2177, we reach 60 billion people based on some of these models, and that's the capacity that the world...
No, there's no way we can reach that ever. All of the models for carrying capacity are anywhere between as low as 10, but I would say 12 to 15. 12 to 15 billion. And we were at 1990, we were at 5 billion. Now we are at 7.4 billion. Yes. So the population is growing. I mean, we are minute to 12 in terms of population for the planet. That is given. And we don't have means on spreading to another planet. Even if we had means of colonizing another planet, let's say you find another Earth, and it's not going to solve the issue of exploding population. There's no way, because exponential growth is very fast. So when you are considering, sometimes I ask this question to just get a sense of understanding of the exponential growth. When I ask students to consider bacteria growth in a container, right? You put one bacteria at 12, let's say either midnight or noon, and the rate of splitting, right, in two is going to be each minute. So after each minute, each bacteria splits in two and becomes two bacteria, right? And then 12 hours later, right, at 12, let's say midnight, you are going to have the entire can filled. So you look for the bacteria that will split that way and fill this type of a can. At what point in time? So what is the clock? What time the clock reads as this is filled halfway?
Like, for say, like, with the population model of it, what happens after you level up? Is there ever a time when it goes back down?
That depends on which method of competition we employ to compete for the resources, and then you read between the lines.
Okay. So once you reach a certain capacity, it's not something, there's still variables that can fluctuate that number. It just can't
Oh
go
yeah,
above that.
it can't go above that because the planet can't sustain it.
Is that carrying capacity just sort of land, like the amount of physical land that people can be on, or?
No, it's the resources, it's food, it's how much food you can grow on the limited surface area that you have. Oh yeah, you can change, you can put GMOs and you can...
So that isn't a constant carrying capacity that can also change?
Carrying capacity can change, but not significantly.
Okay.
Well, let's consider this. Guys, tell me the time, tell me at what time the can is half full.
Oh,
1 unit beforehand.
So the bacteria splits every minute into two bacteria.
So
11:59?
Yeah, right? Right, so 60.
So each bacteria becomes two bacteria every minute. At what time exactly? So call this AM, call this PM. At what time exactly you are going to have half of the, at what exact time half of the jar is full?
11:59.
11:59, very good. 11:59, because all of this will be filled with bacteria. At 11:59, every bacteria in this half will split. The population doubles. The population doubles every minute. Understand that. So minute before midnight or whatever is going to be, right? Now, you send one brave bacteria to find another can. And the brave bacteria finds another can. Great. Sends back the signal to other bacteria to come over. At what time is the second can full?
What's the rate at which they're coming out of it?
It's the same, right?
Same, yeah. Same rate.
Is that 11:59 p.m.? Or, yeah, what,
I am.
would it be a.m.?
Minute after, very good. So if this is 12 p.m., 12:01 p.m., and this is why population cannot be rectified by, oh, here's another planet like Earth, let's just move there. Look at the rate. You have half of the can minute before 12, and then at 12 the can is full, You find another can and at 12:01, that can is full. How many cans do we need at 12:03? No? 8 cans. At 12:03, you need 8 cans. Well, that means what? In another 200 years, we need 8 planets? Do you see the issue? You actually have to go to population clock website and observe change in population and understand that that model is ticking all the time.
There's a website.
Of course there's a website. There's a website for everything.
I didn't know that.
There's a magazine called Walking. Just think about that. Entire magazine, put one foot in front of the other. And then the running one, which is just do the same thing except faster. They talk about shoes and things.
Did they talk about going to the microwave to put in pizza and then coming back in the walking
I
one?
have no clue. I would rather watch paint dry.
Is there a magazine for that?
There's probably a magazine for that as well, exactly. I know. Anyway,
So then what is the solution? Do we know, or do we just start limiting things?
the solution for population?
Yeah.
Nothing. We're just going to die out as a species because
So, yeah.
there's no solution. You have to actually debate global warming. That's the end of discussion of this species. It's our end because we have to debate that. We have to discuss because some people don't get it. That what we do now with carbon emission is not killing the planet, it's killing the ecosystem that supports our life. And all of these brilliant scientists that say, oh, it's not a big problem, they have to understand, they don't get it, that 3/4 of the extra temperature is absorbed by oceans. And if you guys didn't see the, what is the coral, but yeah, but what is the name of the documentary? I think it's called Chasing Coral. That is your thing to watch tonight and get depressed forever, all right? Because you can see the global warming killing the whole ecosystems. And then when the ocean ecosystem is dead, guess who's next? Exactly, because everything is connected. So there is no debate at all. As soon as you start debating the global warming and you have someone backpedaling, and you start debating the population issue and you have someone backpedaling, you're just signing the death warrant for the entire species. And the planet is going to just go around the sun. It was fine without us. It is fine with us, and it's going to be fine without us again. All right? If we as a species want to survive, we have to immediately, but then we vote these imbeciles in the office and so on. So, yeah, there you go.
And then isn't the longer we wait,
The worse it gets.
exponentially more difficult it will be to
Exactly,
cross?
because look at our models. They're exponential, right? All of the models are exponential. So the longer you wait, the worse it gets, and the clock is ticking. And where are we? It's 5 to 12, right? That's where it is with population. Just go about and look. 1990, 5 billion. 2017, 7.4. Carrying capacity models vary from 10 to 15 depending on, it's a lot of factors, and a lot of scientists would propose the other ones, but I haven't seen a paper that had carrying capacity of the planet go over 15. And some say that those are really unreasonable carrying capacities because 15 billion people on the planet where the global warming is melting the poles, oceans are warming up and rising, so you're losing land mass, right? And we don't breathe underwater. And also deserts are always expanding. I don't know if you know about that concept, but the wind carries the sand, so the deserts are expanding as well. So you have exactly. So the plowable surface, right, where we can live, is decreasing every year because the oceans are expanding and the sand is expanding. So we have less surface area to live on and grow food on, and we have exponential explosion in this, plus the species are dying off due to global warming. Welcome to Earth.
That's why you just, and then I keep my food cold. So,
Make the Earth bigger?
make Earth bigger. But how is that possible?
But didn't you just lie about the bacteria? Like, what the
I'm
hell?
not a scientist, it's not up to me to figure it out.
Yeah, I know. Well, all we need is that gun from Despicable Me,
Yes.
except we need to reverse it. The one that shrinks the moon.
So we gotta turn the polars.
Yeah, we have to turn the battery backwards, yeah, and shoot it at the Earth, maybe make it bigger. I know.
I think we got this solved. There we go.
Yeah, I think we figured this out.
There we go, that's the extension.
Yeah.
I'm just colonized on the moon. We already were there before, so we can go there again.
Colonize the moon?
Yeah, we'll find a way.
What are you gonna do with the gravity of 3 point whatever it is?
I'll jump all day.
Yeah, but then these children and children's children are just going to be weaker and
Oh,
weaker
no,
and
no,
weaker.
I
and
said
then-
I'll colonize the moon. I'll just stay there. You guys can all suffer on Earth.
But the children and children's children are going to be so weak that they wouldn't be able to live. You might be okay, but...
Did you just solve the problem? Wait, hold on. Maybe we have a solution for all this.
Inverted skyscrapers?
What?
The ones that go under the ground?
Ground scrapers.
Ground scrapers. That's great.
Can they be
At
both?
least the people that will be building iPhones can't jump off of them.
It'll be an inquake.
Yeah, I know.
It can't possibly fall. Yeah, it won't fall if we're inside it. Gravity doesn't go up.
It'll crack.
What? Just turn off.
And then eventually, at some point in time, you will be wondering why you have lava in your living room.
Because of gravity.
No, we're inside the Earth. It cancels out.
Yeah. Yeah, keep thinking.
Cancel out, right?
Keep thinking. A lot of stuff cancels out. Exactly.
If we have a drill that can get that far.
The entire section of the lecture on doomsday versus the extinction is playing with the constants of this equation. There are no new equations. It is analysis that you would apply upon the model that we already have. So yeah, just read it.
Is this model pretty accurate for most things, like most populations?
Yes, because you are going to reach. So this is it. The one that has the carrying capacity, birth rate, death rate, and the constant of sustainability. Yeah, I said it. That model is the one that would be appropriate, and then you can employ that model with animals as well, with technically anything else, because if you introduce a species that is not native to a certain ecosystem, that species would flourish. It would be amazing for them, right? Because they would have most likely no natural predators, but they would eat technically everything around.
Right.
We made those
We've
mistakes.
done that.
Yeah.
Because we tried to get rid of something, which then backfired, and then
And
we
you have
ended up
issues.
having too much of that.
Exactly.
And then we tried to figure out something that can eat that, and that backfired again.
Wasn't
So
Yeah.
there a problem with like? I think this was like.
I think there are a few cases in Australia and so on. Yeah.
Something.
So you don't touch ecosystems that way. I mean, you can hate spiders all you want. Without spiders, will be drowning in other bugs. You can hate snakes all you want, but without snakes, we will be drowning in mice and rodents, which snakes are eliminating around. So, everything is needed and everything is necessary, and us hating, certain species because whatever stupid reason, it really damages the ecosystem in that, right? So you get, all these mungas to kill all these snakes, And then when mungos are done with snakes and you have extinction, which you can actually show in this model, then you have the mungos, which is going to mangus. Is it mangus or mungos? Mongooses? Mongooses? I don't know. It's mungos in Serbia, so there we go. Yeah, that thing is really evil. I mean, that. Yeah, it has good reflexes. If you ever seen mongoose or whatever fight a snake, snakes are pretty damn fast.
Oh yeah.
And this thing is faster.
Yeah. What's your feeling on mosquitoes though? Like.
Well, when it stings, I have to scratch it. That's the feeling that I have.
Yeah.
That's the feeling.
Those without any consequences.
No.
Of course.
What do you mean no? What are we gonna get rid of that?
I know I read ahead, and I know I read it, like you said, to prepare for class prep. It says on page 39.
Guys,
Page 39. Reaching the 60 billion that some demographers believe to be the maximum for which the planet can provide adequate food supplies.
no way.
Thus, the
Where is it?
2177, page 39.
You say 60 trillion?
60 billion.
60 billion?
60 billion people or 60 million species?
Example 5.
Where? I'm sorry. Can
Page
you?
39.
Page 39.
Right in the middle.
Uh-huh.
Yeah, we have the same book. No? Part C. And then at the end.
When was this book made?
Yeah. Wow.
Yeah.
There's no way.
Census.gov. How can there?
I've never seen numbers this high. I've seen up to 15 billion most.
They take the census every 10 years, right?
Yeah.
I got it.
So when
Yeah.
did you make this census? Like how long?
No, this is again one of the carrying capacity papers. So I would have to actually chase this down and see where what was proposed and how, and how viable
This is
that
not
would be.
true then.
Well, it might have
Again, it's going to be a view of a scientist who computed it, and then you have to see whether it's you have to take everything that science does, grain of sand, and you look into it, and you look for the supporting evidence, because we are bombarded with the pseudoscience and terms that mean nothing and so on. You have to filter everything, not just everything that I say, everything that media says, everything that you read. You find one scientific paper that starts screaming about something, it's one scientific paper, you might as well not have it.
Fake math?
No, you can do math. I can set any number.
It's not
That's
big
what I'm
math.
saying.
I mean, calculation is calculation. We can talk about 150 billion if you want to. It's not an issue at all. The question is there a scientific paper? Are there many scientific papers that are showing the same claim?
Do they
That's
take
the
into
question.
effect like the
Yes, they do.
idea of global warming and all that? Not near, because if that was back in the 90s, they probably didn't have that big of an effect as they do now.
Well, it says 1999, I believe, or
Yeah.
something.
So that's what, 17 years, 16, 18 years
18
from now?
years ago.
So that's still a long time from really making a big deal of global warming.
212,000 people a day are born. So
Yeah.
Sorry, what was that, Ellen?
212,000 worldwide.
Well, that's the website, guys. That's the website which I mentioned before.
Census.gov?
No, the World Population Clock.
Oh, population.
It is census.gov, but there it is.
That's, so right now we're at 7.424 billion. And we're-
Wow, that's going as fast as the debt clock.
No, not that fast.
Yeah, not that.
Where's our death clock?
Well,
Yeah.
just count that number.
No, not debt.
We made it to
24
20
hours.
trillion yet?
Oh,
Write down that number right now,
Yeah.
and see tomorrow at the same time, you'll see 212,000 difference.
Well, I think those are worked out, but look at this. One birth every 7 seconds, one death every 12 seconds.
Oh, so there's more deaths than there are births.
Yeah, no, every 12 seconds.
Oh,
So,
there's more birth than, so for
yeah,
5 seconds
so
off.
14 seconds, right? 14 seconds, 2 kids, and in 12 seconds, 1 died, right?
Another baby.
Right, I got you. That's how you look at it, I was looking at it. 1 international migrant every 32 seconds.
Exactly. So yeah,
One birth every second.
Oh, so there's the net gain of one person every 12 seconds.
yes. It tells you that this is more of the United States. Where is the the world top populous countries? China, India, United States, Indonesia, Brazil, Pakistan, Nigeria, and there's Japan, 126 million.
That's what I got. 12,342 for one birth every 7 seconds in one day.
United States.
Well,
That's
the
US.
United States statistic has to do with we accept a lot of people in immigration, in spite of what you hear in the media. We do allow a lot of people to come to this country, so that's not necessarily our indigenous population. That's what bumps us up that because our population is leveled off from the rest of the country.
Which indigenous population you're talking? Because there are two steps there.
Way back, like the ancient Asians that came here 10,000 years ago.
Okay.
There was like 5 of them over a land bridge thing. You know.
2 on a boat with all the animals.
Yeah.
I know.
Yeah.
All right.
That one out genetically. Well,
I didn't know India had that many people. That's a lot of people.
India's
Yes, it is.
China, aren't they?
Well, look at it.
I can't see it.
Yeah.
Yeah,
Those are the real numbers. So you see it. All right. Well, that's all that we have on population. You guys, if you want to, you could research more and dig deeper into these concepts. It gets to be depressing. If you want to see a little bit about the effects of global warming, take a look at the documentary. It's called Chasing Corals. And yeah, it's that bad. It's on Netflix. To quickly for a quick reference. So what do we have? We have 5 minutes left, right? And then another 30 after that. So shall we jump into acceleration velocity models? Yay, exactly. So let's start. I will restart the stream.